All right, now we're going to fill out our learning card for conditional probabilities. So conditional probabilities look like this. Whenever you see this type of symbolism, the probability of A and then this vertical line B, that's a conditional probability. So that's one thing to consider. So we're going to look at the probability of A given B. So taking a look here, that notation says this. This is the probability of event A given that event B has occurred. So our two events are going to be A is going to say wealthy, somebody is wealthy, and B is saying that they are a thrift store shopper. So this is the scenario that we have. 97% of people are considered not wealthy. 1% of people are both wealthy and thrift store shoppers. And 88% of people are not wealthy and do not shop at thrift stores. So with that said, I can fill out this table. And when I fill out this contingency table, I have shops in a thrift store and wealthy. So when I put all this together, I get 1% of people that yes are wealthy and yes shop in a thrift store. That's what we have right here. 88% of people are not wealthy and do not shop at a thrift store. So that's 88% here, no and no. And then I can fill out the rest. Since I know that 97% of people are considered not wealthy, I'm going to put 9% or 0.09 right here for not being wealthy. And now this column of not wealthy is equal to 97%, which then means that this last box that hasn't been filled in yet would have to be 2% or 0.02. Well, before I start to use this and before I start to look at these probabilities, let's take a look at the formula for conditional probability. So the probability of A given B is equal to the probability of A and B. This symbol right here is this symbol for intersection, which is and. The probability of A and B divided by the probability of B. Okay, so this is the formula that I want to use down here for these two probability questions. If A and B flip spots, then all of the A's and B's up here would flip spots as well. So another rule that we have is that the probability of, this is the multiplication rule, the probability of A and B is equal to the probability of B times the probability of A given B. So that's another useful formula that is derived from our conditional probability formula. So let's take a look at these two probabilities down here in the corner. So looking at the probability of A given B, that means we want to say what is the probability of being wealthy given that they are a thrift store shopper. So again, the probability of being wealthy given that they are a thrift store shopper. Well, I'm going to use the formula here. That would be the probability of being wealthy and being a thrift store shopper divided by the probability of being just a thrift store shopper. And that turns out to be this. The probability of being wealthy and a thrift store shopper is right here at 0.01, yes and yes, divided by the probability of being a thrift store shopper alone, that would be 0.01 plus 0.09, which is 10%, or 0.1. So the probability of A given B, which is the probability of being wealthy, given they are a thrift store shopper, is equal to the probability of A and B, wealthy and thrift store shopper, 0.01, divided by the probability of B, which is the probability of being a thrift store shopper, which is 0.1 or 10%. And the math turns out to be 0.01 divided by 0.1, which is 0.1, which is 10%. So I repeated myself there a couple of times, but I really want to emphasize the fact that you should just trust your formula. Now, if we have a two-way table like this, a contingency table, one thing that we can do is we can kind of cover up what we don't want. So this says the probability of being wealthy given they are a thrift store shopper. So we don't care about those that are not thrift store shoppers. So I could cover this up. Oops, let's undo that. What is happening? Sorry for those of you that are watching the video and you're trying to figure out what's going on. I just want to take this, look at the properties, and I want to fill it. There we go. So as I look right here, I am covering up those that are not thrift store shoppers. And so what is the probability of being wealthy given that you are a thrift store shopper? Well, it's 1% out of the total of 10%. So that's one way that you could look at that, or an additional way that you could look at that question. Well, what about the probability of B given A? So what if we say the probability of being a thrift store shopper given that you are wealthy? Well, that would be, let's flip-flop these, the probability of being a thrift store shopper and wealthy divided by the probability of A, which is the probability of being wealthy. So once again, using our formula and trusting our formula, the probability of being a thrift store shopper, given that you are wealthy, would be the probability of being a thrift store shopper and being wealthy divided by the probability of being wealthy. So that would be the probability of being a thrift store shopper and being wealthy is 0.01. And the probability of being wealthy that we're going to divide by in the denominator is 3% or 0.03. So 0.01 divided by 0.03 is 33% or 33.3%, which is 0.3 repeating. So once again, this can be a little bit confusing. And what we really should do, I don't like the fact that this learning card uses A and B here. I wish they would use like W and T. I think that would be a little bit better to use those variables here, especially for this particular given problem. But if you have questions about this, you can ask your teacher in class. But I really think that if you go back and watch go back in the video and talk through this one again, this would be the probability of wealthy, or I should say thrift store and being wealthy, divided by the probability of being wealthy. And there's your probability. But what if we don't have a two-way table? So I used a two-way or contingency table here to answer these two conditional probability questions. But what if we don't have a two-way table? Well, using a tree diagram can be very, very useful. So let's take a look at this scenario and use a tree diagram to help us out. All right, well, let's set up the tree diagram first. So what we can see is that we have the entire population of the school, and there are drugs and people that are doing drugs and people that are not doing drugs. So drugs and no drugs. Now it tells us up here that 15% of the students are on drugs. So on drugs is 15% chance. No drugs is an 85% chance. Then we move on and it says during a drug test correctly identifies the presence of drugs 95% of the time. So if a person is on drugs and they get tested, they are either going to test positive or they're going to test negative. If a person is not on drugs, they could still test positive or negative. So if a person is on drugs and they take the test, 95% of the time, it's 95% accurate, they will test positive. That's why 95% is here, which means that people that are taking drugs will test negative 5% of the time. Then it goes on to tell us that 3% of the time it incorrectly gives a positive reading when a student is not on drugs. So if they're not on drugs and they take the drug test, 3% of the time, or 0.03, there will come back a positive test. And 97% of the time it will come back as a negative test. So now we can use this tree diagram to help us answer these two questions below. But before we do that, I'm going to go ahead and multiply these probabilities for each one of these branches. So if I were to say, what is the probability of being on drugs and testing positive, I would take 15% times 95%. If I wanted to know the probability of being on drugs and testing negative, it would be 15% times 0.05 or 5%. and so on and so forth for each one of these branches. So I'm going to go ahead and multiply these out and find the probability of each of these 4 different scenarios. All right, so I've multiplied it all out. So the probability of each one of these branches is given right here. Now, one of the nice things about a tree diagram is that you can add all of these probabilities together, and if the sum of each one of the probabilities for each branch is equal to 1, then you have most likely done your work and set up your tree diagram the correct way. And this is the case. If I add 0.1425 plus 0.0075 plus 0.0255 plus 0.8245, I'm going to get 1. So I've got 100% of all the different scenarios that could occur. But now what about this question? What percent of students will be falsely accused of drugs? Well, if they are not taking drugs, this question means they are not taking drugs, but they test positive. So no drugs, test positive is 0.0255. So the probability for this question right here is 0.0255. So what about this second question? Overall, what percent of test results are incorrect? Well, there's 2 situations that can be incorrect. You could have a student on drugs, but they test negative, or you could have a student that is not on drugs, but they test positive. So I have these 2 probabilities here that are both incorrect results. So what I need to do is take 0.0075 plus 0.0255 and add the 2 together. And when I do that, I end up getting a probability of 0.033. So here's just an example of using a tree diagram and using conditional probabilities, because each one of these probabilities that I'm finding based off of the tree diagram could be considered conditional probabilities. In other words, like, what is the probability that a person does drugs given that they tested positive? Or what is the probability that a person tests positive given that they do not do drugs? You could find those probabilities using this formula, but you can also find these probabilities down here using your tree diagram. So hopefully this has been helpful, and you've learned a little bit about using a two-way table, a little bit about conditional probabilities or given problems, and a little bit about using a tree diagram. I hope you have fun in your stats class.